Today we're going to talk about nuclear chemistry. So this weekend, I was at Martha's Vineyard. So Martha's Vineyard is it's an island off the coast of Massachusetts, so near Cape Cod. So you can see I have it on the map. So this is Martha's Vineyard, and we stayed at the Vineyard Haven. So there's a little port here. You can see there's a little inlet of water. So the only way to get to the island really is by plane or by a ferry, interestingly enough, that goes between the island and the mainland. So I actually just recently learned about this. So the Senator Ted Kennedy actually drove off a bridge near Martha's Vineyard. So that was called the Chappaquiddick incident. So here I took a picture of the ocean. So while I was at Martha's Vineyard, I stayed at a place somewhere out near the woods, and because of that, it was very dark outside. There was no real light pollution. As a result of that, I was able to get some pictures of the stars because I stayed up until like 4 at night because, the past weekend was the Perseid meteor shower. So there's a big comet that goes around the sun called Comet Swift-Tuttle, and it leaves a trail of debris that actually intersects with the path of the Earth's orbit. So once a year, the Earth crosses through the debris path, and the debris enters the atmosphere where it glows and it vaporizes, which causes meteor showers, which you see as light going across the sky. So I saw like maybe 6 meteors. Yeah. So the Perseids in particular are rather spectacular. So I was able to get this picture of the stars. So you can see this constellation is a W shape, so it's called Cassiopeia. And I'm not sure what the other stars are, but I know that constellation pretty well. So yeah. So the question is, what makes the stars shine? So what makes the stars shine? What makes the waves go? Basically, and really, what provides the energy for everything that happens on Earth? So it provides the energies for trees growing, the breeze, so like the currents that birds soar on, the movement of the waves, everything. This is all driven by nuclear chemistry. So, and of course, how the stars shine, and even some of our electricity. It's all created by nuclear chemistry. So, stars, right? So stars. So the sun is a star. So here we have a false color image of the sun, and the sun is a ball, a almost perfect sphere of plasma. So in earlier lectures, we learned that atoms consist of protons, neutrons, and electrons, where the protons and neutrons are bound together in the nucleus, and the nucleus is surrounded by electrons. However, in the plasma state, the electrons are not associated with atoms. So the nuclei and the atoms and the electrons are all separate. So this occurs at very, very high temperatures. And it turns out you can make plasma in a microwave by cutting a grape open, cutting a grape in half, and leaving a small sliver of grape peel connecting to 2 halves. You put this in the microwave and you'll see plasma, but I don't recommend you do that. Yeah. But if I remember correctly, the light that's created during a lightning strike is from plasma, probably, because of the immense heat generated. So the sun is a ball of plasma, and so the sun releases 3.846 times 10 to the 26th watts of power. So to give you a sense of perspective, so imagine you had like, I'm trying to do the math in my head right now. So imagine you had 1 trillion light bulbs, right? So 1 trillion, so imagine you gave everyone on Earth 1,000 light bulbs. So you gave everyone on Earth 1,000 light bulbs. Then, so you would have about 1 trillion light bulbs. You would have to multiply that by 1 trillion times to get the amount of energy that the sun is producing. Okay? So this is an immense amount of power. And the sun also weighs 1.989 times 10 to the 30th kilograms, which is a huge number, unimaginably huge, in fact. And all of this weight is trying to come together under the force of gravity. So the sun has to support this immense weight, and so the energy that the sun produces actually pushes on the mass within the sun, which keeps the sun at an equilibrium, what's a so-called hydrostatic equilibrium. And this immense power that the sun produces, so 3.846 times 10 to the 26 watts of power, sustains all the light on Earth. So all of the energy that you use in your day-to-day, with maybe the exception of nuclear energy, can be traced back to the sun. So coal, for example, most of our electricity comes from coal, and coal comes from comes from dead plants and animals from millions of years ago. And the energy that those plants and animals used came from other plants and animals, which eventually came from sunlight, right? The energy that plants use, all of the plant matter comes from sunlight, a process called photosynthesis. Wind power. So wind power is generated by winds, and those winds are generated by rising air, and that air rises because it's heated by the sun's energy. So all energy really comes from the sun. And if you think about it, the energy that is used in a nuclear power plant comes from supernova, right? These very heavy elements like uranium are only produced in very energetic processes like supernovas. Okay. And one other thing I wanted to mention is that the sun is releasing this huge amount of power, but at the same time, the sun is also expected to last for billions of years more. So maybe 10 more billion years. So somewhere in that range. So the sun is outputting this immense amount of power, and it has to do this for an unimaginably long amount of time. So as you can imagine, there's a huge amount of energy there. And here I have a picture of the star WR124. So this is what you would call a Wolf-Rayet star. And this star shines 1 million times brighter than the sun. Okay? So this is one of the brightest stars in the universe that we know of. So the question is, where does this energy come from? So before we answer that question, let's look at a review of the nucleus. So the nucleus is the center of the atom. And the nucleus is held together by the strong force. So the strong force, which is between nucleons, so neutrons and protons. So the protons are all repelling each other, right? Because they're all positively charged. And like charges repel. However, we also have neutrons in there, and the protons and the neutrons help contribute to the strong force. So you want to have the right mixture of protons and neutrons to hold the nucleus together. And usually the nucleus is very, very stable. So like I would say that maybe the nucleus in your water in the air, the nucleus in the oxygen atom in the air has existed since the beginning of Earth, right? And the hydrogen nuclei in your glass of water have probably lasted since the beginning of the universe. So the atoms, the nuclei that make up everyday matter have lasted for much longer than the age of the Earth, which is something to contemplate. So the nucleus cannot be altered through chemical reactions. However, some nuclei are radioactive, so they spontaneously will change. So they will so we call this radioactivity. Additionally, nuclei can be changed or transmutated in very energetic environments. For example, an old decaying star or a supernova. Okay? So, no. And remember that the identity of the element is determined by the number of protons, so the atomic number. And if you have the same number of protons, but different amount of neutrons, it's called an isotope, okay? So what are some uses for radioactivity? So nuclei are unstable. So when they decay, you get so a big nucleus disintegrates into smaller nuclei. You get, for example, we get a huge release of energy. So here I have a picture of a nuclear power plant. So this would be an example of a controlled release of energy. So using, we control the rate of radioactive decay so that it's slow enough that we can easily and safely use it to generate electricity. Here I have a picture of an atomic bomb. So this is a picture from the Trinity test, which is the very first atomic nuclear weapon ever tested. So this is an uncontrolled nuclear reaction. So what happens in the atomic bomb is that you have uranium or plutonium atoms, and when one of these atoms gets hit by a neutron, it breaks up into smaller atoms, but it breaks up into smaller nuclei. But while it does this, it also emits some neutrons. We also get some neutrons, and these neutrons go on to bombard more atoms, right? So eventually you get this runaway effect, and all of the atoms are falling apart in this huge release of energy. Whereas in a nuclear reactor, we have moderators and control rods, which allows to control the rate of neutrons being emitted. So the extra neutrons can get absorbed by some material. So this means that we don't immediately get this runaway chain effect. We can keep it very stable. And radioactivity also finds applications in medicine. So here we have an apparatus that generates the radioactive substance technetium 99, I think, technetium 99 from molybdenum. So, and then this technetium will immediately be shipped off to some hospital to be used for imaging or something like that. So radioactivity also finds use in medicine. So you may have heard of the equation E equals mc squared. So Einstein's very famous equation. So what does E equals mc squared mean? So this is what we would call mass energy equivalence. Okay. Mass energy equivalence. And the idea is that mass and energy are really the same thing. So mass and energy are the same thing. And you can relate mass and energy to this equation. And c is the speed of light. So c equals 3 times 10 to the 8th meters per second. So c is a huge number. So what this tells you is that energy equals mass times some huge number, right? So this means that you can get a huge amount of energy from a very small amount of mass. So you might be asking, so where does the energy in a nuclear reaction come from? It comes from the mass. So for example, if we have an atom A decaying to atom B plus atom C with some release of energy, the mass of B and C will actually be less than that of A. I guess you can have a real example. So if we have like so let me see. I have a periodic table somewhere, right? So in a process called the proton chain. So proton chain. So what happens in this reaction? So basically, to summarize, we have 4 hydrogen atoms, hydrogen nuclei, and then this goes to a helium nucleus, and then plus it says positrons. Yeah, so plus 2 positrons. And a positron is just like have you heard of antimatter? So a positron is the antimatter equivalent to an electron. Okay, and I'll explain more of these symbols later. So if we look up the mass of a hydrogen atom, let me see what it is. I need a very exact value. So I need a really exact value. Okay, here we go. So you can see here I have a very exact value. So 1.007825 AMU. Okay. And let's say the helium atom is, let's see. So 4.002602 AMU, so atomic mass units. And the positron's mass is so small we can ignore it. So now what we can do is we can find, so the mass of everything on this side is 4 times 1.07825 equals 4.0313 AMU. So you can see that there's actually a slight decrease in mass. We're going from 4.0313 to 4.002602. And the difference is what we would call the mass defect. Mass defect. So it's what we can convert this mass defect to energy. So, so we also call this the nuclear binding energy. So the nuclear binding energy is the energy that goes into holding the nucleus together. So, so let's see. So in this case, we have a mass defect of 0.0287 AMU. Okay. So let's just say we had 1 mole of this. Okay. So we have 4 grams of hydrogen nuclei. Okay. We have 4 grams of hydrogen. So then we would get a mass defect of 0.0287 grams. And we have to convert this to kilograms. So that equals 2.8698 times 10 to the 5 minus 5 kilograms. And we can plug this into E equals mc squared. And then, so that equals 2.8698 times 10 to the minus 5 times 3 times 10 to the 8 squared equals 2.58 times 10 to the 12 joules. So 2.58 times 10 to the 12 joules. So this is a huge amount of energy. So for comparison, a hamburger probably will contain about 10 to the, so one hamburger, a large hamburger will probably contain about 10 to the 7 joules. So this is like 10,000 hamburgers, okay? So just by turning 4 grams of hydrogen into helium, we can generate the amount of energy that's contained in 10,000 hamburgers, or no, 100,000 hamburgers. Okay, so this is where the huge energy that's released in a nuclear explosion or in the star comes from. Okay, so yeah. So I just wanted to, you don't need to know the details of that calculation. I just want to illustrate how much energy is really being produced in these kinds of situations. So there are several different kinds of radioactivity that I want you to know about. So the first one would be called alpha particles. So these are helium nuclei. And these are represented by the Greek letter alpha. So a lot of heavy nuclei, for example, uranium, thorium, americium, near the end of the periodic table, tend to emit alpha particles because this lowers the, so they emit alpha particles. And alpha particles are actually rather harmless, relatively harmless, and they can be stopped by a sheet of paper about. So when they were investigating uranium ores and stuff, they were actually detecting helium gas, and this helium gas comes from these alpha particles, because the alpha particles will eventually collide with the air molecules, they'll slow down, and they'll pick up electrons to become helium atoms. So I believe that in some old-fashioned smoke detectors, I think they've been replaced by newer technology, but in the past, you have a small sample of americium, and americium is a radioactive element. So americium will emit alpha particles, and these alpha particles can be picked up by a detector. So let's say there's a fire, then the fire will produce some smoke, and the smoke will interfere with the path of the alpha particles. So the detector will detect that less alpha particles are getting through, and it will sound the alarm. Okay. Next, we have beta particles, indicated by the Greek letter beta. So a beta particle is just an electron that's moving very, very fast. So beta particles are also relatively harmless. So you can probably stop it with like a sheet of cardboard or something like that, or some aluminum foil. So beta particles are high energy electrons. So if you have a nucleus that has a very large number of neutrons, then it will tend to emit beta particles in a process called beta decay. So if you have a very large number of neutrons, because these neutrons, we'll talk about this later, neutrons, they turn into protons when they emit electrons. Okay. Yeah. And then finally, we have gamma rays. So gamma rays are extremely high energy photons. So, you know, a photon coming from the sun versus a gamma ray. The gamma ray might have 1 million or 1 billion times more energy than the photon coming from the sun. So incredibly high energy photons. And you really, it's very, very hard to stop gamma rays. You need maybe like several feet of concrete to stop a gamma ray. So gamma rays are similar to X-rays, actually. X-rays are slightly lower energy. So if you've ever had to get like an X-ray of your teeth done, you have to put on this very heavy bib made of lead, and that helps to stop the X-rays. So gamma rays are like X-rays, but higher energy. And gamma rays are produced in a lot of different nuclear reactions, mainly so fission. So when the nucleus splits, it releases some neutrons and some smaller nuclei along with some gamma rays. And a transition from an excited nucleus to a ground state nucleus will also release a gamma ray. So yeah. And this picture is kind of interesting. So we have, let's say we have this radioactive source that generates all three types of particles. And we put this in a magnetic field. So alpha rays are helium nuclei. So do you think they'll be positively or negatively charged? So do you think alpha particles are positive or negatively charged? So an alpha particle is a nucleus, right? So are nuclei positive or negative? Right, positive, because the nucleus contains protons, which are positive, and the neutrons don't do anything. So alpha particles are positively charged. What about beta particles? Do you think beta particles are positive or negative? Negative, right, because they're electrons, and electrons are negatively charged. What about the mass? So which one do you think is heavier, an alpha particle or an electron, or a beta particle? Right, so alpha particles are going to be much heavier. So we can illustrate with this diagram. So we have a source that emits these different rays, and we place it within an electromagnetic field. So the alpha rays are deflected in one direction, and the beta rays, because they have an opposite charge, are deflected in the other direction. Furthermore, alpha rays are much heavier, So they have a higher inertia and they're harder to deflect, so they don't deflect that much. However, the beta rays are very light and they're very easy to deflect. So they deflect a lot. And gamma rays are not charged at all, so they just go straight. They don't deflect at all. So if you see the medal that was dedicated to the Chernobyl liquidators, this kind of image is on it. It's quite a nice design. Okay. So the main, I think for AP Chemistry, the main thing you need to know how to do is to write nuclear reactions. And nuclear reactions are actually pretty easy to write. They're much easier to write than normal chemical reactions. So I want to review the isotope symbol. So in the isotope symbol, we have the chemical symbol of the element, right? And we have these two numbers up top and bottom. And the lower number is the atomic number, or the number of protons. And you can even think about this as like how positive charged, like the positive charge. And the mass number is equal to the number of protons plus the number of neutrons. So because mass is roughly conserved, the sum of the mass numbers on one side should equal the sum of the mass numbers on the other side. Conversely, the sum of the atomic numbers on one side should equal the sum of the atomic numbers on the other side. So here, we have 92 and 90 and 2. So 90 plus 2 equals 92. 234 plus 4 equals 238. And some minor things I want to talk about. So where's the pen? Here we go. So let's do neutrons first. So the mass number of a neutron is simply 1 because the mass number is the number of nucleons. And the atomic number is 0 because neutrons are neutral and no protons, okay? And here's where things kind of get a little bit confusing, because what happens if we have a beta particle or an electron? So either way is correct. So the mass number is 0, right? We have the mass number of 0 because they're very light. They don't have the mass of a nucleon. And we usually like to write the atomic number as -1. Because the charges have to balance out, basically. So it's convenient to write it as -1. And we can also have a positron, which is written as beta plus. And instead of a -1, we write a +1. And here's the other symbol. So I want you to write down these 5 symbols. Yeah. And sometimes you'll see HE written as alpha. So as alpha and then 4, 2. So you might see it written like this. So the Greek letter alpha. Okay. So I'll give you a minute to write that all down. Okay. So we can go into further detail. So let's just do some specific examples of the different kinds of decay. So in an alpha decay, we emit an alpha particle, which again, we use the alpha letter or He, okay? Or helium. So in this generic equation, you can write this down if you want. We emit an alpha particle, and the mass number is decreased by 4, and the atomic number is decreased by 2. Notice that 2 plus Z minus 2 equals Z, right? 4 plus A minus 4 equals A. So this follows the rule that we explained before. You can see we have a parent nucleus decaying to a daughter nucleus plus an alpha particle. Okay? In beta decay, we emit an electron, which is written as a beta minus. So, okay. And so this follows this rule. So again, we write it as 0 and minus 1. So 0 plus A equals A. And negative 1 plus Z plus 1 equals Z. So you can see we have essentially a neutron turning into a proton. You can give it that way. And finally, we have gamma emission. So we emit a gamma particle, which is 0, 0. And we write a star next to the excited nucleus. So this nucleus is an excited state, which is kind of complex. It goes into the nuclear shell model. But you don't have to take notes on this, but basically the idea is that similarly to how electrons fill energy levels, the protons and neutrons also fill energy levels. But that's a bit out of the scope of this class. So we have an excited state, and it goes down to this lower state. And because we're going to a low energy state, we have to release energy in the form of a gamma ray. So notice how A and Z are unchanged. And I do want to mention positron emission. So positron, this number, so you can ignore the VE thing. This is just a neutrino, and neutrinos have an incredibly small mass. So yeah, basically all you have to know is that beta decays will produce either electron neutrinos or electron antineutrinos, but let's not worry about that. So this E plus, it's a positron. So we have 0 there and plus 1 here. So notice 23 equals 23 plus 0, and 12 equals 11 plus 1. Okay. So, okay. So I have some problems here. I'll just do the first few. So in the first example, we have uranium. Okay. So we have, where's my pen? Okay. Let me get the pen first. Okay, so we have uranium 292 and 238, I think. Let me just make sure that's right. Yep. So, and this goes to a mystery thing, plus an alpha particle. So we can write two equations. So let's look at this first. So we have A plus 4 equals, so this stuff, the side on this stuff, equals, and then that has to go here, equals 238. And we have, likewise, can someone tell me what the second equation should be? What should our second equation be? Right, exactly. Z plus 2 equals 92. So we solve for A and Z, and we get that it should be X, and Z is 90, and A is 234. And now we need to figure out what X is. And to do this, all we need to do is go to the periodic table. And we need to find atomic number 90. So that happens to be thorium. So this should go. So the answer is thorium 234. Okay? Let's do another example. So let's do this one. So can someone tell me what A should be in this case? 0. And what about Z? Right, -1. Now, does anyone remember what particle has these characteristics? Remember, it has a mass number of 0, so it should be very light. And this tells us it has a -1 charge. So it should be a beta particle, right? Because the beta particle has a mass number of 0 and a charge of -1. So our complete equation should be okay. And the final one, I just wanted to mention this. So we have silver 180, and it's an excited state, and often this is just represented by an M, and it goes to its ground state. So the mass doesn't change, the atomic number doesn't change. All that happens is a release of energy. So this is simply a gamma particle. So I'll give you like 10 minutes to do the last 3, okay? So all we need to do is add these 2 numbers and then add these 2 numbers. We get uranium 236. What about this one? Helium, and then we take the difference of these 2 numbers and the difference of these 2 numbers. And additionally, you can write helium, which is fine, but you can also write an alpha particle. You can write the alpha symbol if you want. And what about this one? Yeah, exactly. So the difference of 3 and 0 is 3, and then difference of 1 and -1 is 2. Okay, so we get helium 3. So let's see what time it is. What time is it? We want to be able to predict whether a nucleus is stable or not. So I have this very interesting chart here. So you can see that the dots labeled in black represent isotopes that are stable. And depending on the color, you have a different half-life. And what's interesting is that there are actually a very small, there's not many nuclei that are actually stable. Okay. And the ones in blue have decay very, very quickly. So they might decay in like 10 to the minus 5 seconds or something like that. So, and some of these isotopes are extremely rare. For example, like at any given time on on Earth, there might be only a handful, only a few atoms of francium, for example. So, on the other hand, elements like tin, so tin, I believe, is right here. So tin, they have a huge variety of stable atoms, stable isotopes. So the question is why? And one major important factor is the neutron to proton ratio. So as you can see, we've graphed number of neutrons and number of protons, and it kind of curves upwards. So the more protons you have, you need a lot more neutrons to have a stable isotope. But for the light elements, so up to around calcium is right about here. So up to about calcium, you can see we have a very close to 1-to-1 ratio of neutrons to protons. Okay, we have a 1-to-1 neutron to proton ratio. So a radioactive decay will tend to bring the nucleus back to this optimal neutron to proton ratio. What I mean by this is that if we have a lot of neutrons, some of those neutrons will want to turn into protons. And in the process, they release electrons. So this is beta decay. If we have a lot of protons, then some of those protons will want to turn into neutrons. And so the nucleus will either undergo positron decay, a positron emission, or beta plus decay, or electron capture, where the proton captures an electron and becomes a neutron. And for the very heavy elements over here, these will undergo alpha decay. So this brings it closer. So these elements, they undergo alpha decay, which brings them back over in this direction. So going from here to here. So alpha decay. So using this proton to neutron ratio, we can predict whether an isotope will be stable and what type of decay mode it will undergo. So yeah. So I just want to talk about the rate of radioactivity. So radioactive decay is a first order process. So does anyone remember the integrated form of the first order rate law? This was from a while ago. So you might want to look back at your notes. This is from a very long time ago. So you might not remember. But so the integrated form of the first order rate law is like so we have remember right? Or you can think of it as this way. So here we use concentrations. It turns out that when we're talking about nuclear decay, it's much easier to think about it in terms of number of atoms. Where N is the number of atoms. So radioactive decay is a first order process. So so this means we have a constant half-life. And it turns out for radioactive decay, it's very useful to talk about half-life. So recall that half-life is equal to the natural log of 2 divided by the rate constant. And for radioactive decay, we use a unit called the becquerel, which is 1 decay per second. Okay. So, okay. Let's just give an example. I'll just do an example. Oh, I need to clear all the annotations. Give me a second. Okay. Okay. So as an example, let's say we have carbon 14 goes to nitrogen 14. Let's say we have this reaction. Okay? So, and there's a reason why I picked this reaction. And I believe, if I remember correctly, the half-life equals 5,400 years. Let's say we have 1 million, so 10 to the 6 of carbon 14. Now, the question is, how many of these will be left after, let's just say, 30,000 years? Okay? So the first step is to calculate K. So K equals sorry, equals ln 2 over T1/2, which in this case equals equals 1.28 times 10 to the minus 4 per year. Okay? So now what we can do is we just need to use this formula. And this equals 10 to the 6, right? Because this is the initial amount of carbon atoms. So this goes right here. And then, so we can easily find this. So 10 to the 6 times E raised to the power of negative 1.28 times 10 to the minus 4 times how many years? It's 30,000. So we get so we can say that after 30,000 years, we will only have 21,400 atoms. So let's say we want to calculate the radioactivity of this sample of 10 to the minus 4 atoms of carbon 14 in becquerels. The problem is that becquerels is in units of seconds. So we need to convert years to seconds first. Times, so 365.25 days in a year, times 24 hours in a day, times 3,600 seconds in an hour gives us so 1.7 times 10 to the 11 seconds. So we calculate K equals ln 2 over T1/2 equals okay. And let's just use a more realistic scenario. So let's say we have, I don't know, 1 milligram of carbon 14. Okay. So 1 milligram divided by 14 grams per mole equals, so let's say we have 7.14 times 10 to the minus 5 moles, okay? And becquerels is in decays per second. So we don't want moles, we actually want the number of atoms. So we need to multiply this by Avogadro's number to get the number of atoms. So equals 4.3 times 10 to the 19. And then we can simply multiply this by K to get so 1, 2, 3, 4, 5, 6, 7, 8. 1.75 times 10 to the 8 decays per second. Okay? So you can see that if we just have a very small sample, only 1 milligram, we still have a huge amount of decays per second. Okay. So a more realistic situation, we might only have maybe 1,000 becquerels. So 1,000 decays per second. And by the way, so these decays are often picked up in what's called a Geiger counter. So if you've ever seen like a movie or like a TV show or something, stereotype is like the beep, beep, beep. And the more radioactive it is, the faster the beeping gets. So it's a Geiger counter. Okay. So, yeah. So what's the use of all of this? Well, one major use is radiometric dating. So you might have seen like, oh, so-and-so lived 2,000 years ago, or scientists discovered a plant from 1 million years ago. And the question is, how did they figure this out, right? Because obviously there were no scientists 1 million years ago to write down that this plant lived 1 million years ago, right? So how did they figure this out? They use radiometric dating. And so this is often, if we find like some ancient artifact, we can use radiometric dating to determine its date. And this is really accurate, right? So radiometric dating is actually very accurate. So we can get within like maybe a few years of the correct date. So how does this work? So let's talk about carbon-14 dating, which you might have heard of. So the sun emits this cosmic radiation, and this collides with the atmosphere, generates neutrons, and this collides with a nitrogen atom to form a carbon-14 atom. And plants and animals constantly absorb carbon dioxide. So while you are still living, you're incorporating carbon-14 into your body. So for most living things, the amount of carbon-14 remains relatively constant. But then after the animal or plant dies, they no longer take in carbon-14. So the amount of carbon-14 will steadily decrease. And by comparing the radioactivity of a sample with that of a living organism, we can determine the age of the sample. So we measure the radioactivity comparing to some relative standard. And by looking at this graph, we can determine the age. So if something had 50% radioactivity, it would be this old. If it had 10% radioactivity, it would be this old. Yeah. So you can see we have this, the living organism absorbs the carbon-14, then it turns into a fossil, and the amount of carbon-14, it stops being regenerated, so it decreases according to this graph. And then you can analyze a small piece of this fossil, and then you use a Geiger counter or radiation counter to determine the radioactivity. So basically just counting the number of decays. So maybe it measures, 5 decays, and then you compare that to a normal sample, and that's how you determine the age. The problem is that you can see that after a certain time, there's very little radioactivity. So this is not really easily measurable. So for samples that have been for a longer amount of time, we use different forms of dating. So for example, uranium dating. In uranium dating, you measure the amount of lead compared to the amount of uranium, which helps you determine the date. And there's also dating methods based on around potassium and rubidium. So this is how we can determine. So this is how, like, if you go into the Museum of Science or something like that, and they say, oh, this rock is 2.5 billion years old, this is how they figure that out. Okay. Radiometric dating. Okay. Okay. There's one topic I want to talk about. This is a little bit more advanced, but I thought it's a little bit interesting to talk about. So while I was in Martha's Vineyard, I met a retired professor named James Pritchard. So he's actually one of the founding fathers of MRI. So every day MRI saves like hundreds of lives, thousands of lives. So MRI is an incredibly powerful tool. And it turns out that MRI has its roots in the nucleus, okay? So MRI is very closely related to the idea of NMR. NMR spectroscopy, which is used by organic chemists all over the world. So the idea behind NMR, which stands for nuclear magnetic resonance, is that these nucleons, the protons and neutrons, have a certain amount of what we call spin. So this is similar to electron spin. And this means that certain nuclei, which we call NMR active nuclei, will have a certain magnetic moment. So these nuclei act like tiny bar magnets. So for example, carbon-13 and hydrogen are both NMR active nuclei. Okay, so because they have this magnetic moment, if we apply them to a very strong magnetic field, we get two energy levels. One of the energy levels, it's aligned with the magnetic field, and one of them, it's opposite to the magnetic field. So depending on which orientation it is, it's either high energy or low energy. And we have this difference in energy. Okay? So this difference in energy corresponds to a certain frequency. So usually in the radio range. So these nuclei will resonate at this certain frequency given a certain magnetic field strength. So that means what we can do is we can tune the magnetic field strength until the frequency matches up with some frequency, until the resonance of the nuclei matches up with some frequency. And by measuring the magnetic field strength, by controlling that magnetic field strength, we can record it. And depending on the chemical environment of that nucleus, so depending on what's around that nucleus, it will have a certain, the magnetic field strength will be slightly different. So it's very small difference in the order of parts per million. So this is why often on a chart, it will be recorded in parts per million, because it's a very small difference. Also, and to get this small difference, we need these huge magnets. You can see the guy at the top of the machine. So we have this huge magnet. So a lot of universities will have these multi-million-dollar machines that the chemists use. And these huge superconducting magnets, and they're cooled by liquid nitrogen to keep them cold. So this generates the huge magnetic fields that are necessary to get this splitting in energy. So what you do is you take a little tube filled with your sample and you drop it into the machine, and it spins very, very quickly to help average out the signals. And yeah, so NMR spectroscopy, and MRI stands for magnetic resonance imagery, and it's a very similar principle to NMR. So you might have seen a picture. So the guy flies down on this, on a bed kind of thing, and the bed goes into the machine, which is donut shaped. And that donut shape is like you have these magnets inside the machine that spin very, very fast. and these very powerful magnets, which are cooled by liquid helium. So this is why in the MRI room, you have to remove all metal objects because they'll just get stuck to the magnet. Okay, so you have to like remove all the metal carts. You have to remove like your watch because it will just stick to the magnet, the huge liquid helium cooled magnet inside. So in MRI, they take advantage of the fact that hydrogen, which is in every water molecule in your body, is also is NMR active. So they take advantage of that fact. So we still have about half an hour left. So I think now maybe we can look at some practice problems. So I know that if I have it on the image is kind of hard to see. So I decided to use some online ones. So here I have some online questions. So I guess you can just say A, B, C, D, E, and let's just go through them. And let's just see what you guys pick, and then we can see what the overall score is afterwards, okay? So what do you think one is? What do you guys think one is? And the proton. So we have Z. So can someone tell me what this should be? Plus 0 equals 79 plus 1. Right. So I think that's the correct answer. So we'll just pick it for now, and we can see what you can see what they say later. So let's clear the annotations. So what's the product? So we have lithium-7 combines with deuterium, and we eject a proton. So what should the product be? So what's this? Okay, so I think so. Yep. So let's select that one. What about this one? Yeah. And that question is a little bit strange because I think it should be 4-2 each E. I don't know why I don't know whether you should include I don't think you should include the 2 plus. Let me see what they say. Because no one puts the 2 plus, like, so it's probably not that. So yeah, I think you're right. It should just be that. No one puts the 2 plus. I've never seen that. We could check. is produced when phosphorus 29 decays to silicon 29. So, okay. So we have phosphorus, which I believe is 15. And then, okay, so we know it needs to be a beta particle because of the 0 there. But this should be +1, right? Because, okay. So it should be a positron, not an electron, but close. What about this one? Half-life. We know that the fraction needs to decay by 1/2. So we have 3. So we know that the half-life is 288 days. So 264 divided by 88 is 3 half-lives. So we have 3 half-lives. And it decays by half, decays by another half, decays by another half. So we have 1 gram left. Okay. Now for this one, what isotope would be best? So we want something with a half-life that's similar to about 60 years old, because otherwise either the radioactivity will be so weak or it won't, or there's not enough difference from a regular sample to actually determine anything. So in this case, it turns out that cesium is the best choice because it contains alkali metals. So yeah. So which of the following is most damaging when ingested? This one's a little tricky because remember I said that alpha particles are usually harmless, and that's because they can be stopped by the skin. But however, once they're inside the body, the alpha particles are very heavy, right? Alpha particles are very heavy, so once they get inside the body, they can actually do a lot of damage. Okay. So calculate the energy associated with the alpha decay of 199 bismuth. So this is a little bit tricky. So I think we can skip this one for now. But remember, all you need to do is find the difference in masses. Then you need to, and then you can convert that to energy. They already give you the energy conversion, actually. Okay. So when 249 californium is bombarded with boron 10, you get 257 lawrencium. So what do we form? So let's just do this. So we have californium is 120, 98. Oh, that's still okay. So 98 plus boron is 5. Okay, and 103. So can someone tell me what A and Z should be? Right. So we have 2 and 0. Just very strange because there actually is no particle with these numbers. But what I want you to notice is that if we take the neutron and we times 2, we get this. You get 2 and 0. So this actually corresponds to 2 neutrons. So, and notice they say particles, particle or particles. That's not ridiculous. Okay. So I don't think, yeah, this is not a, yeah, that's not a reasonable question. Um, yeah. Basically the point of this question is like, so the phosphor will absorb energy, but then it will, at some point, it will release that energy in the form of light. So it's phosphorescence. And what about this one? Which of the following can be done to shorten the half-life of the radioactive decay of strontium-90? Half-life is a property of the nucleus itself. And remember that the nucleus is really distinct from any chemical process, chemical or physical process. So it turns out that none of these will actually influence the half-life of the radioactive decay, okay? Because the nucleus is kind of by itself, okay? I think we have some more problems here. Okay. So we have this isotope. So scandium-2140. So what do you expect? This isotope undergoes radioactive decay. What do you think the radioactive decay will undergo? So here we have the belt of stability. So these isotopes are the stable ones. And we locate, so the proton number is 21 and the neutron number is 40. So that's somewhere over here. And you can see this is far above the belt of stability. So we have way too many neutrons. So we want to increase the number of protons while decreasing the number of neutrons. So we convert a neutron to a proton, okay? So decrease the number of neutrons and increase the number of protons. What about ytterbium-177? So by the way, ytterbium is element number, let me see. 70. It's element 70. So we have element 70 and 177, which is kind of ridiculous, actually. Right? Yeah. It's very strange. Oh, okay. Oh, I forgot. Wait, so actually, this is neutrons plus protons, so we need to take a difference of here. So this should be, so we have 19 neutrons, okay? That's my bad. So we have 19 neutrons. So it's somewhere around here. So it's somewhat below the belt of stability. So we want to, increase the number of neutrons. We want to increase the number of neutrons while decreasing the number of protons, which is not an option. So we can just go with increase the number of neutrons. So increasing the number of neutrons or decreasing the protons will both work. But here we have increased the number of neutrons. Okay. So here we have ytterbium-177 and atomic number 70. So the number of neutrons is 177 minus 70, which is 107. So you go to 70 and 107. So 107 is somewhat above the belt of stability. So because it's above the belt of stability, we want to turn we have extra neutrons, so we need to turn those neutrons into protons, okay? So neutrons turn to protons by emitting electrons. So we should have beta emission, okay? Yeah. So what about this one? So lithium-8 decays to beryllium-8. So what type of decay do we have? beta decay because we're increasing the number of protons, so we've turned a neutron into a proton, so we have beta decay. Let's undo that one. So what about this one? I'll give you a second to do that one. You just need to think about it for a little bit. So 1 million atoms, and we have a rate of disintegration of 225. So that's like, so that means we have like, so n equals 1 million, and we have a decay rate of 225. So that means that since k equals the decay rate, we can find k, and k equals 2.25 times 10 to the minus 4. And then we have that T1 half equals ln 2 over k. And then that equals 3080 seconds. However, it asks for in minutes, so we convert it to minutes, and it turns out it's 51.3. Okay. So a cyclotron. In a cyclotron, you have particles confined by magnetic fields, and they go around in circles very, very fast. So this is to try to, so you can create energetic ions. So what's that? So what about this one? What's an alpha particle? Helium nucleus. Particles of helium nucleus. So it's helium-4. So we have 2 protons because the atomic number is 2. So we have 2 neutrons because 4 minus 2 is 2. Okay. And so nuclear fission is when you have a large nucleus breaks up into smaller ones. It does produce steam, so that's how a nuclear reactor works. Yeah. And we don't need to know about the details of how nuclear reactors work. Okay. I don't think the rest of these questions are super useful. So yeah, so nuclear chemistry actually isn't super complex. The main thing I want you to just remember is that the sum of these numbers should be the same on both sides. The sum of these numbers should be the same on both sides. And I think if you can remember that, that's really all you need to know. That's really the heart of what you need to know for AP chemistry. So I don't think I have anything else to discuss. So I think we can end a little bit early. Okay. So the next 2 lessons will just be review. So we'll just be doing review problems. Okay. So, yep. So see you guys